We are ready. So today I am sharing our work on one of the key challenges in digital twin, that is ensuring the fidelity at runtime. This is a joint work with my research directors, Javier, Troya, and Vallecillo. And no, okay. Digital twin as a changing our way of interacting with physical assets. We use them for many things like design space exploration, predictive maintenance, behavior optimization, or even anomaly detection. But as these systems grow more complex, things may go wrong. So these are the kind of things that we want to avoid. We want to avoid real-world mistakes caused by inaccuracies in digital twins, and that it was the main goal of our first paper, which was this one, which was recently accepted by DSE, so if you want to check. And in this paper, we wanted to measure the level of fidelity between the physical and the digital twin to ensure that the behavior was accurate. And how we did that? Well, first of all, let's define fidelity. So fidelity is the degree in which the model is able to reproduce or replicate the state of the system. And our algorithm is based on trace alignments, and is based on two of the main sequence alignment algorithms presented in bioinformatics. And these alignment algorithms are BLAST and Needleman-Bunch, and they are used to align nucleotide sequences, which are sequences of DNAs that are characters. And in these alignments, they included both gaps and mismatches. So for example, in this first alignment, we can see that there is exactly one gap here, which means that there is one character that is missing in the first sequence. And if we go to the second, we can see that we have three mismatches, which are three characters in the first sequence that are different to the second. But these algorithms are used to detect the level of similarity between these chains. So how can we apply this to real digital twins? Because mostly the state of the digital twins is defined by numerical values. For example, we have here two robotic arms, and these are the positions in X, Y, Z of the point of the gripper. So in case of the sequence of characters, it's easy to determine if two characters are the same. An A is clearly an A, but it is not as easy when we are dealing with numerical values. So somehow we need to define a threshold in which two values cannot be considered similar anymore. So in this case, based on our experiments and the different use cases, we realized that this value is usually 3 times the measurement accuracy of the instrument. So we have now the traces, the threshold, and our algorithm, and then we get the alignment. So this is the result for these two traces. And we can already see here what is really the difference between these two traces. So as in the previous slide, we have sequences of gaps. And what does this mean, these gaps, in this context? Well, as we can see, there are more snapshots in the physical twin than in the digital twin presenting similar behavior. And in this case, this means that the physical twin is moving slower than the digital twin, assuming that these snapshots are taken with the same sampling rate. Well, we took assuming, now let's take a zoom out. This is actually the full scenario of these traces. So the robotic arm is going down, taking an object, going up, moving, and then going down and leaving the object. And you can see here the trajectory and the alignment between the different snapshots. So the points that are aligned, these are the ones that are sufficiently similar, and when we see spots without any alignments, this means that these places are not close enough to be included in the alignment. And we can see already here how the movement of the digital twin is faster than the physical twin. But we would need to check every alignment to see these characteristics. How can we do this generally and to compare with different alignments? We have 3 fidelity metrics which are the percentage of matched snapshots, which are the number of snapshots which are aligned. Then we have the Fletcher distance, which is the maximum distance between trajectories, and then we have the Euclidean distance, which is the average distance between match snapshots. And with these values, we will be able to compare different alignments. But this was for full scenarios. This is our previous paper. Now it's about how to apply this algorithm to runtime monitoring. Well, using a sliding windows was our idea. And this means analyzing only the end latest snapshots that we are getting from the systems. So let's change to a different example. Now, instead of a robotic arm, let's go to an elevator, in which we have a commercial simulator called Elevate and a physical elevator. We actually got the data from the acceleration of the elevator. From the acceleration, we can get both the position and the speed, which is what we need to measure the fidelity of the movement. So this is the trace of one scenario in which the elevator goes from the 4th floor to the ground floor and then back up. So here we can see the negative acceleration of going down and the positive acceleration of braking before arriving to the ground floor. And then we have here the alignment. So we can see some difference already. These are sequences of gaps that are pointing to a delay in the behavior of the physical twin, because the movement of the physical twin starts later. And then we can see some mismatches which are different between the traces. And this means that there is a small anomaly here, if we can see it. And that could be an anomaly that is different, but it's actually a normal characteristic of that elevator, because they include an additional acceleration just to improve the user experience. But let's slice this and apply sliding windows. So if we take 100 snapshots from here, this is the alignment we get, and we can still detect the delay. And if we keep moving the slide window forward until the anomaly that we mentioned, we can also see how the delay is still noted and how the anomaly is detected. But again, we will be having to check alignments once and again and again and again. So let's go to the metrics. What metrics could be used to detect this automatically? So in this case, we have the percentage of match snapshots, but we can also reason about the percentage of gaps and the mismatches. So we are dealing with this specific window, and these are the statistics. So these 20% of gaps are talking about the first delay that we mentioned before. And since the snapshots are taken each 0.1 seconds, and we have 100 snapshots in this sliding window, we have a delay of 2 seconds. And if we can keep moving the window forward, this is a part in which the acceleration is constant for both the physical and the digital twins. We have 100% of the snapshots. But if we keep moving forward to the anomaly, we can see that the percentage of mismatches is 5%, meaning that we have an anomaly of 0.5 seconds. That would be all. So to sum up, we have an alignment algorithm to analyze the scenarios. We apply sliding windows, and we are able to detect both delays and anomalies in real time, and also diagnose them. So what it is for the future work? Well, we want to define some alarm thresholds just to automatically determine if we have an anomaly. We want to play with the window size, because in these examples we are using 100 snapshots, but we would have a wider window or even a narrower one. We want to check performance and runtime to check if it is feasible, and we finally want to try with all the digital twins. And then this is when it comes to you. We would love if you had traces of digital twins that are currently working and would need validation. Please ping us, send us the traces, we can help you. Or even if you wanted to try our tool, well, it's publicly available. We have it in our repository here in the paper. That will be all. Thank you. So if you have any questions.